Okay. Today, I guess I'd like to talk about one of my favorite things. Oh, wait, hold on. So I've got a chat. Um, okay. Okay. So there's a question of which was interesting about how wrong the pollsters were on the elections and stuff like that. Not yet emotionally ready to discuss such things, but it's a very interesting, it's an interesting phenomena that you had a lot of people trying to predict what a lot of pollsters. The problem was not really pollsters. The problem was not really people trying to aggregate the polls so much as the polls themselves seem to give very surprising results in the election. And it's interesting to figure out why that is. I don't. I was reading a little bit, and this is still a debate. One thing is, of course, like if you are a site like Nate Silver's site, where you're aggregating the poll data, if all the polls are wrong, then you get the wrong answer. I I will also say that Nate Silver kind of said that, we were kind of within one standard deviation of polling error of this being a very competitive election. And that's kind of basically what happened. Why are there polling errors? Again, I'm just riffing here. One question is if you poll the wrong people, okay, you really need to try to construct, one of the hard parts about polling is to construct samples of, make sure that you're talking to a representative mix of random voters, of voters. And this is a very hard thing to do. The usual way that they have done this historically is call random phone numbers. They would dial random streams of digits. And, based on who answered the phone, that would be a fairly random process. But it's illegal to do that to cell phones. And most of you have cell phones and not landlines now. So it's a lot harder. That's one of the reasons it's hard to get representative samples. Another reason it's hard may be that the people don't like talking to the pollsters and aren't saying what they really are going to do. It's possible that it could have been a late shift. People suddenly changed their mind, but that I think is probably not really the case here. It probably has something to do with not constructing the right sample, okay? And that's being a fairly hard thing. Any questions about polling? I guess if that's what people are interested now, just as a quick, warm up while I'm waiting. Well, since we were running a little bit late. Any questions? Okay, fair enough. So what I'd like to talk about today is one of my favorite topics, actually, which is nearest neighbor methods. So we've looked here in the last several classes, we've been looking at, certain machine learning methods. We looked at linear regression, which is a way of trying to predict the value of a function given data. We looked at classification. We looked at logistic regression as a technique for classification. And again, that was sort of going to create a linear function that the score of which was going to be used to predict what label it had. Nearest neighbor classification is and as we will see, regression also kind of works, is a quite different sounding technique that I find kind of appealing, okay? Basically, assume we are in a world where we have a large amount of, a large amount of representative examples, okay? Let's say, again, this I think is my data here that I usually talked about. This is height. One of them is height, one of them is weight, okay? I have points labeled by, either being male or female. We'd like to try to come up with a classifier that would try to tell, given a new point, Okay, is it male or female? What is the idea? With nearest neighbor classification, we would like to kind of carve up space into regions, okay, around each point, and basically take as our label, okay, for a point, the label of our nearest neighbor. And, you know, again, there's several variations, like how many nearest neighbors we use and what distance function and things like that. But there's several good things about the kind of thinking in terms of nearest neighbor classification. One is that it's a very simple technique, okay? It doesn't require any fancy math or anything like that. You simply take your point and then figure out what your query point and find out what the labels are of the points around you. So it's simple. I find that it's very interpretable, in that if you want to ask why we came to it, why did we decide that this point was this point was blue? Well, it's because its neighbors were blue, and we could look at our neighbors and see, you know, were they representative blue cases? You know, is it interesting? So I claim it's interpretable. I also claim it's kind of inherently nonlinear. Remember when we were talking about logistic regression, we were looking for a separator. A separator in logistic regression, it would have to be a line. And if it was a line, it would be the straight thing. The separating, the decision boundaries that we can form with nearest neighbor techniques can be arbitrarily crinkly and nonlinear, and, you know, don't have to satisfy a particular preconceived idea of what the shape of it is. So nearest neighbor classification is a good thing. Any questions about that? And I like thinking in terms of nearest neighbors as a way to validate, you know, again, an important part when we're building different models or different representations is to validate, is one way of doing it better than the other? And we usually do this by kind of building some kind of an error function. You know, we separate our training from our test, and we build an error function, and you know, we see if you have two different ways of doing it, you see which one has a better average error. What I like about nearest neighbor methods, the idea of nearest neighbors, is they give us a way, when we look at what the nearest neighbors of points, this to me is a great way to evaluate things, because it kind of gives you a real way to look at your data and to get a sense of what it's doing right or what it's doing wrong. So to kind of motivate that, there was a problem we were working on where we wanted to try to find representations of websites, okay? A technique to take essentially the network of the web, you know, different websites, and reduce each vertex on the web, meaning a website, to a vector representation. And there were two ways of doing it that we were interested in. And I want you to tell me which one is better, not by looking at an error metric, but by looking at representative examples, and tell me whether it's better or not. And maybe we'll see if we agree, and maybe we don't. So what was the idea here? I am going to show you for each of a certain number of queries, what were the 10 nearest neighbors to it in two different representations. There's one of them was deep walk, one of them was rand-NE. When you look at the universities, which representation is better? Okay, this is an opinion subject, so I'd like to hear some debate. Which one of these representations do you think is better at capturing what Stony Brook means?
I think the deep walk is better because it has city and state of New York schools, whereas the rand-NE has all throughout the country schools.
Okay, so one thing you're saying is, you look here, these are CUNY and what's CUNY schools?
CUNY and SUNY, yeah.
And SUNY schools. And the other ones, Barnard and Colgate and Hunter, are all in New York. So we know what the meaning here is, okay? What about the one for Rand and E? Does anybody see any organizing principle here? Do these seem as closely, I would say, does anybody, to me, the idea that the nearest neighbor of Stony Brook is Binghamton makes a lot of sense to me, because Binghamton is, is another big state university, right? Okay, what about comparing, if we look at the nearest neighbors of Baidu, okay, which one do people like better? Does anyone like one better?
Deep work.
Why do you like deep walk better?
Because the deep work looks to me they're all Chinese website. I'm also familiar with that than the Rand and E. So
Right.
I think deep work better, yeah.
So this one is a better, this one you're telling me they're all kind of prominent, this is a prominent Chinese, I gather, search engine company. Many of these other ones are clearly Chinese, I will say social media and related type companies, okay? So people like that. And what about on the other side? What do we see next to Baidu? We see a kind of, it looks like a relatively motley, random group of things. Alibaba maybe makes sense. That's a big Chinese company. But it's not obvious to me that the second closest thing to Baidu should be free patents online, right? What about when I look at Chase? Does anybody know what chase.com is? What is Chase? Does anyone know what Chase is?
Chase Bank.
Chase Bank, it's a bank, okay? So which one of these, which do people think is better?
Deep walk.
You think deep walk. Why is deep walk better?
I see a lot of other banks in here.
I see some banks. I see other things dealing with money, right? That's probably one's probably a bank. This and this is an investment company. So yeah, so these look like they're dealing with banks and money. What about on the right side? Okay, I'm seeing a bunch of companies, but this seems to be a travel company. Those seem to be two travel companies. This seems to be a Delta is an airline. UPS and FedEx are both shipping companies. Okay, I like deep walk better. Does everybody agree? What about Wikipedia? When we look at wikipedia.org, what do you think of the nearest neighbors? Which one do people like better?
Deep walk again, because it has all the wiki.
You're saying it's finding all these wiki things, okay? And these look like information sites. Here, again, I seem to be finding smaller things. I don't, I guess many of these, again, look sort of like reference sites, but that's a comic strip and that's a question site. So yeah, so I think I like that better. Does everybody see how when you have an example where you know something about what you're doing, looking at nearest neighbors gives you a way to evaluate it? It may not be a, you may not be able to quantify it particularly. Again, if you want to quantify it, you go and you look at 10 of these and you keep track of how many times did you like one better than the other. And now you've got, I guess, a statistic. But this kind of qualitative evaluation is better. And again, in fact, I do feel pretty good about deep walk being better than this other method, Rand and E. Why is that? This is kind of showing, we'll talk about clustering, I believe it is next class. But this is showing the websites clustered by what their last domain is. We colored, every dot is a website. the color of the dot depends upon what the last extension is, .com, .edu, .jp, okay? And when I look at this thing, these clusters clearly are a lot tighter, okay, than what we get from RAND-NE, okay? So all in all, I'm happy to say Deep Walk, I think, is better than RAND-NE, and I'm a little bit biased because Deep Walk was a technique we developed, okay? And maybe I'll talk about it a little bit in a later class. But did everybody see how the nearest neighbor things give you a way to interrogate whether or not, what your thing looks like, and to give you an appropriate, a way to get a qualitative evaluation? Any questions?
Yeah, I have a question.
Yes.
What was the input graph used for these algorithms? Like, what did it encode?
Okay, so we will talk about this a little bit later, but a way to think about them is you could think about it a little bit like if we took the adjacency matrix of the graph. This isn't quite how it worked. These worked, but in principle, if we took the adjacency matrix of the graph and we did an SVD on it, remember when we did singular value decomposition? For every one of the vertices, we would get a lower dimensional vector that would presumably represent the original adjacency matrix of the graph. So you can think of each of these methods as doing something like SVD. So we got a smaller representation. So let's think that we could have done it two different ways. Okay, these are two different smaller representations. And then we could find the nearest neighbor because these are now just vectors, two vectors. Okay, each vertex is represented by a vector. The distance between two websites would be the distance between two of these vectors. Okay, so you can think of one of them as being again, something like singular value decomposition. I will maybe tell you more later. The other one here is essentially a random projection where I basically multiply this by a random matrix. I take the adjacency matrix and I multiply it. If it was n by n, if I multiply it by, I guess, an n by k matrix, excuse me, an n by k matrix, I will get an n by k matrix just like I did with singular value decomposition. Actually, if you do this multiplying by random numbers, you will actually get a reasonable representation. Suppose, let's say you have a row in an adjacency matrix, and this is a vertex. And a second vertex has a very, very similar, but not exactly identical adjacent set of vertices it's adjacent to. When we do the dot product of both of these by the same random vector, we're going to get a number that's very similar. So I'm going to talk a little bit about a random projection type of thing a little bit later. But you can actually build interesting representations there. I've gotten a little sidetracked from what I'm doing, but any questions about that?
Well, and my question was more centered on what would compose an edge in your input graph. Assuming we're
dealing with the web graph, a typical web graph would be if you have a website, what websites does it link to? So suppose you crawl the web, okay? If you go to to Skeena's page, you're going to find that I'm going to have a link to Stony Brook. I'm going to have a link to the computer science department. I'm going to have a link to my various course pages. Okay, I'm probably going to have a link to the publishing companies of my books. Okay. The input was for every website, what does it link to? That gives us an adjacency matrix. And by doing some kind of manipulation on it, we can find a lower dimensional representation for that adjacency matrix. Does that answer your question?
Yes.
Okay. Any other questions about this? Okay, so I use all this to try to motivate the idea of nearest neighbor methods. And one thing that one thing that is essential in a nearest neighbor method has to do with identifying what our distance function is, our distance metric. And we are what you call it. And so a distance function like the Euclidean distance has certain properties that we kind of assume of distance functions. Okay, what is the distance from a point to itself in you know, what you call it, in Euclidean distance? What is the distance between a point and itself? It should be 0. That much should be clear. Okay, distances are always positive. If you say, what is the distance between me and my car? Okay, it is going to be, you know, a certain number of 100 feet. Okay, but it's never going to be negative. So distances have the property that they are always positive. Okay, we know that distances are always positive. We know that there's also this identity point, that the distance from x to x is always 0. We know that distances are always symmetric. The distance from me to you is the distance from you to me. Okay? And we also know that distances satisfy the triangle inequality. What does that mean? It means that if I am given a point here, and a point here, and a point here, the distance from x to y, okay, is always going to be less than or equal to, okay, the distance from x to z plus the distance from z to y. When we think about distances, there's this notion of as the crow flies distance, okay? And the direct route is always the way you minimize it. So the distance from x to y is always less than or equal to going through the path going through any intermediate point. Any questions? When is it equal?
When all the points lie along the same plane.
Well, same plane or line. Basically, if we move z so that it actually is on the line between the, you know, from x to y, then actually we wouldn't be going out of our way, but there's no way to make it smaller by going through an intermediate point. Any questions? So these properties are what you call it, are, you know, what we, any distance measure that satisfies all of these properties is called a metric. And metrics, you know, kind of, we're used to thinking about distance functions as metrics because we live in the earth. We're used to thinking about Euclidean distance, okay? And, you know, it makes it easier to reason about things if they're metrics. That said, many of the similarity measures that we have talked about in here, okay, are not distance metrics. When we measured the what you call it, the correlation between two things, okay, if they were very, very similar, the correlation was 1. If they were as different as possible, okay, the correlation would be -1. Does everybody see in what way does this fail being a metric? Well, it's certainly not true that what is the distance from a point to itself if we use the correlation metric? Again, by point, I'm going to say again, you kind of thinking that you've got a point in d dimensions is like a vector of d numbers. Okay, and if you have a second point, if this is P1 and P2, the correlation would be comparing each, you know, each position simultaneously. What is the correlation of a point with itself?
1.
1. It's not 0 anymore. So this is clearly not a metric, and it can get negative. And it also means something like the correlation from X to Y. You learn very little about it in terms of properties from correlation from X to Z and the correlation from Z to Y. God knows how they relate to each other, okay? So correlations are similarity metrics, they're not distance functions. Cosine similarity, meaning the dot product, the normalized dot product, the cosine of the angles between points, vectors, is also not a metric. There are certain mutual information measures, okay, that are used to compare probability distributions. You could think of a probability distribution as for all different values of X, what's the probability of X? And so you get a vector like this. And there are various information measures like KL divergence, which I'm not going to talk about. But these things are often not symmetric. Okay, that the divergence from me to you is not the same as a divergence from you to me. Okay, these other two are symmetric, but otherwise not a metric. Finding the cheapest, suppose we have a set of points that are airports, and we have an edge, and the weight of an edge was between every airport, and the edge was the cheapest airfare to get from me to you. Okay, cheapest direct airfare to get from me to you. Is that a metric? Certainly, we know that the distance between any 2 points, is it going to be positive? If the distance is the airfare from me to you, is that always going to be positive?
Yes.
Yes, so they're never going to pay you to go to an airport, right? Is the distance from me to me 0? The answer is yes. Okay. Is it symmetric? Typically it is. It fly from me to you and you to me. It's usually the same thing. But does the triangle inequality hold when it comes to airfare prices? Has anybody ever been looked for an airfare where the direct flight might have cost $1,000? But if you fly through, if you fly through, Iceland or something like this, you might be able to get there at a cheaper cost. Have people experienced such things?
Yes.
Okay, good. Okay, so that would not be a metric. Okay, what is the mother of all metrics? The mother of all metrics is the Euclidean distance metric, okay? What is the Euclidean distance metric? If I want to find the distance between 2 points, and again, I think of a point as being measured by an array of dimensions. So here there are d dimensions, okay? And each point has d different values where the order of the values matters. The Euclidean metric basically sums up the squares of the absolute differences of the dimensions. Okay, we don't need to actually make it an absolute value if you wanted, because when you square it, I guess the sign goes away. But what does this do? This is the again the sum of squares of the of each dimension, and we take the square root of it to normalize it. Okay, any questions about the Euclidean distance? This is something obviously you're familiar with. What issues would happen, though, if you try to take the Euclidean distance? Let's say you have 2 points in feature space where they are d dimensions long. What kind of issues might arise in whether the Euclidean distance is a meaningful measure of similarity between them? Any issues? Any ideas?
Sorry, could you repeat the question again?
Questions, I'm just, suppose, let's say I gave you, let's say that we had your height. Let's say we measure people's, we have records of people. They have their height, their weight, and what would be a third quantity about them? Let's just say IQ, okay? And their height was in inches, 65. Their weight in pounds was 132, and their IQ was 17. Next one, we got someone who's got a height of 70, weighs 180, and has an IQ of 100. Does everybody see what I've got now? I've got 2 points in D dimensions. Here, D equals 3. And I could, if I wanted to measure how similar these people are, I could take the Euclidean distance between them. Okay, these 2 points. Okay. Are there any ideas that would make that, any things that might make that a problem?
The features are on different scale.
First of all, the values are on completely different scales. Okay, heights here are inches, weights here are pounds. The tallest person on Earth is going to be, I think, what is it? 12 times 8. The tallest person is probably under 100 inches in height. Okay, by weight, that the heaviest person is clearly, 300 pounds or more. Okay, so the range. Notice that if we took the distance between these two, the amount, people who are differing quite a lot in height, their difference, especially when you square it, might be about a ninth as much of a contribution to the squares. Notice when you subtract the differences of the weights, the potential range would be a lot higher. Okay, and so when you take the differences, the sum of squared differences are going to be a bigger thing. So my first claim is you need to do something to normalize to make the dimensions comparable. Okay, any questions? That might be a z-score, that might be something like that. What is another thing when it came to making a distance? Suppose we have another dimension that was of human experience that was unimportant. What's an unimportant thing to quantify about people? Let's say I want to count the number of fingers that they have. Okay. I guess that's not a good dimension. First of all, I guess because everybody almost always has the same figures. Let's say I had the last digit of their social security number, which is a random number. Okay. Now, you might know from analyzing your dimensions that some dimensions are more important to capture what you mean as similarity. Okay, that are kind of more important to what you're trying to cover. Okay, and if so, you would like to be able to weigh. You might sometimes want to generalize our distance metric by multiplying each dimension by a coefficient to say certain dimensions are more important to me than other dimensions. Okay, this will still leave a metric. So if you know enough about what your data is, that you know that certain dimensions are more important to you than other dimensions, you might incorporate that in your distance function. Okay, but regardless, it's important to normalize things. So you're comparing, the dimensions kind of are given equal treatment. Any questions?
Professor, what if we have a mix of numeric and categorical features in our data?
Okay, now Euclidean distance, okay, is is not good, is expecting numerical values. Okay, if you've got categorical values, that actually represents a little bit of a problem. How could you do it? Well, you could use like a one-hot encoding, okay, where you have different, if let's say if it's a binary label, male, female, or something like that, or some other binary label, okay, would be that you could represent by 0 and 1 as numbers. So that can be encoded as numbers. But again, if you have a multi-class thing, you might want to represent it as, if you have k different classes, you might want to represent it by k different 0, 1 choices, okay, where it's 1 if you're in the kth class. Then you could use something like distance, okay? But it's not clear it works with categorical data unless you do something like that. Any questions?
Thank you.
Okay. Now there's a generalization of the Euclidean distance that is kind of important and interesting, called the LK norm, okay? Now, look at this distance formula. In the Euclidean distance, we took the square of the differences and then the square root, okay? That was the L2 distance. In general, we can have a, for a given k, the distance, the LK norm, okay, is take the kth power of the absolute value of the differences and the kth root of that. Now note that, what does that mean? If you have k equals 1, what is this going to mean? If k equals 1, the power you raise it to is 1, so nothing happens. All you're doing is summing up the differences, okay? So the L1 distance is sometimes called the Manhattan distance, because if you want to figure out what is the distance from one point to another, you simply sum up the difference of the dimensions, okay? So in Manhattan, there's lots of different ways to get from here to here. But if we have, Manhattan's a place where points are on a grid, every shortest path you're going to be going either to the right or up. There's many different things. But ultimately, the number of up steps you're going to take is proportional to the x coordinate, the y value, the difference in the y's. The second dimension here. And to go to the right, it was the differences in the x's, okay? So the K1 distance was the Manhattan distance, okay? Any questions about that? That I think you can see. A little bit harder is, what does we get if we take the L infinity distance, okay? What would be the L infinity distance of a thing? Okay, what are we doing? We're taking the differences of each dimension. Actually, what were the differences? Let's take a look at, let's say this, let's just speculate. Let's try this point and this point. We're going to take the differences of the x's here, which looks like 1, 2, 3, 4, 5, 6. Okay, and we're going to raise it to the infinite power. Plus, we're going to take the differences of the y's, which is 1, 2, 3, 4, and raise that to the infinite power. And then take the infinite root of it. Okay, now infinite is hard for me to think about. But suppose we think of what's going to happen if infinite here means a big number. What do we know is going to happen when we have 6 to a big number plus 4 to a big number? What should be clear is that the bigger difference is going to dominate the smaller one when you raise it to a much bigger, a big power. Does everybody see it? 6 and 4, you may say that's pretty close to each other. But 6 squared compared to 16, well, that's a bigger difference. And if I raise it to the third, that's going to be 6 times 36, which I can't do in my head. But does everybody kind of see that as you raise as the exponent increases, the bigger value raised to the exponent really dominates the smaller value raised to the exponent. So the sum of something big plus something small is essentially just the something big. And the infinity root of 6 to the infinity is roughly 6. So the L infinity distance is basically going to report to you what was the value of the biggest dimensional difference between the points. Any questions about that? Okay. For any value of k, we regulate a trade-off between how much we are concerned about the total dimensional difference. Again, when we add the L infinity thing, any a change of 1 to a small difference was had just as impact as a change of 1 to a big distance. Okay. The LK, the K in the LK gives us a way to regulate what that trade-off is. Any question? So which of the following points is further from the origin? Okay. We could compare 2, 0 or 1.5. Which one of these points is further from the origin? The answer I would like to see is it depends. Okay. If k is equal to 1, we are going to be looking at the sum of the differences between the dimensions. And that's going to be the difference between 2 for P1 and 3 for P2. So P2 by the L1 distance would be further away. For k equals 2, now we're talking about the sum of squared differences. Okay? It turns out these points are almost equally far from the origin, but P2 is closer. When we use the L infinity distance, we worry about the bigger difference, okay? And, in this case, the first dimension differed by 2, the other dimensions differ by 1.5. Now P1 is farther. Does everybody see that your choice of distance metric will change the order of what your nearest neighbor is? If you use a different distance metric, you may very well come up with a different set of nearest neighbors. Okay, any questions?
Do you mind giving a brief overview of k equals infinity again? I kind of didn't understand it.
Well, okay, just mathematically, what is, okay, maybe let's just think about it. What is the limit, I think I'm going to do this right, of if I have x plus y, x plus 1 to a large power, okay, let's say plus x to a large power, okay? This term, x plus 1 to the L, is going to grow wildly bigger than this thing. How does 2 to the, let's just think about it. How does, let's say, 2 to the n compare to 3 to the n? If I sum these things up, the limit as n gets larger and larger is going to approach 3 to the n. Okay? That this term is dominant over that one. Therefore, the sum of these things, if this is a big power, okay, is going to be very, very close to just this term. And if I take the nth root of this term, it's obvious that that's going to return to me 3. So the L infinity distance gives you the size of the difference of the maximum component. What single dimension has the biggest difference between the 2 points? that's what it's going to return. Not the dimension, but the magnitude of the difference as the distance between them. Any questions? Okay. So how would we choose which value of k is it that's more interesting to us? Should we be using the L2 distance because we're used to it? Or should we, what happens if we use a small, okay, you know, a small k equals 1, adding a little noise to any element is going to make the same amount of change in our distance, okay? So if we have a lot of little differences, okay, let's think about what the difference is. Suppose we have a vector in a fair number of dimensions. You know, 100 dimensions is a good number of dimensions, d, okay? If we add a little bit of random noise to every one of the dimensions, that noise will show up on the K1 distance, okay? It's not going to show up, okay, on the K infinity distance. All that's going to matter is what is the one dimension where they differ the most in, okay? And so, and kind of one problem is if you have long, high dimensional points, the distance between high dimensional points is kind of hard to see if there's a lot, if the error, each dimension is measured with noise. Okay, when you have a higher value of k, you can kind of sort of ignore some of that. Okay, that said, k equals 2 is usually a good distance value, but it's sometimes worth playing with it to see what gives you the nearest neighbors that you want to see. Remember, we showed at the earlier how you could evaluate a, you know, something like, let's say, a distance function by taking embedding the feature space you care about. Show me the nearest neighbors with one value of k and another value of k, and decide which distance measure works best for you. Any questions? Another way to think about the LK norms is to think about what a circle is in different dimensions. You think you know what a circle is. Certainly you know what a circle is in L2. In 2 dimensions, you know, with an L2 distance norm, a circle looks round. And why is that? A circle defines all the points that are a distance of r, okay, from the origin, right? And this is why a circle looks like that. In L1 world, this diamond is a circle. If this is a distance of r and r and r and r, note that on the diagonal, if we have the point 1/2, 1/2, r over 2, r over 2, that is also going to be by summing up the dimensions equally. So an L1 circle looks like a diamond. An L infinity circle, okay, are all the points that have a biggest dimension that is equal to r. And as you can see, the circle is this box. Any point on here, the biggest dimension, okay, a difference from the origin is r. And for k between 2 and infinity, you get kind of increasingly square-ish, okay, rounded square-ish, okay, circles, okay? Any questions about that? And like I say, playing with the distance function is something you might want to do when you're dealing with higher dimensions. Any questions about circles or anything like that? Okay. Again, when we take a look at what happens when we did it in SVD? Remember, originally we had, let's say, an n by m feature matrix, and we reduced that okay, through the magic of linear algebra to an n by k featured matrix, where this k kind of is, kind of captures as much as it can in the original matrix. It is often better to compute the distance between things, okay, in the compressed representation than the full one, okay? If you have if these measurements came with noise, typically the act of compressing, okay, the matrix down, okay, eliminated noise. And so it eliminated redundant dimensions. Remember, you had redundant dimensions before. In a redundant dimension, that kind of dimension would count twice, okay, if you were doing a distance, a distance function. So using a compressed or collapsed representation can lead to, I will say, more robust nearest neighbors than you can in the original high dimensional space. Any questions about that? That I hope is kind of believable. And again, as I said before, the LK norms weigh all the dimensions equally, but because they weigh all the dimensions equally, the scale matters, okay? So making sure that you have normalized the values, so all the dimensions are comparable, okay, in the same unit and or whatever, okay, is important. But this is typically why we use a z-score, okay? If you have a complex data set, finding the distance between the z-scores of each dimension, okay, they will have the property that the mean and the standard deviation of each dimension are equal, okay? So we'll treat it like that. Any questions? Okay. So what can you do with this nearest, once you have a distance function, and once you have a distance function, and once you have a set of points, okay, training points, I claim we can do a regression using nearest neighbor ideas. What is the point? Suppose we have points on an XY plane where there is a Z value that we're trying to predict, okay? Every point that we have, okay, is going to be somewhere here. If I want to try to predict what is going to be the value, okay, at a particular point in XY space, if you think about what a regression problem is, it would be trying to predict what Z is as a function of X and Y. One idea of how to do it is to look at just the XY projection of your points and find what are the nearest points to my query. Once I know which points have the most similar XY values to the query, I could then average their Z coordinate to get an interpolation or some kind of either average them or some other interpolation to figure out what, to come up with an estimate for what the Z is for a given XY. Any questions about that? Does everybody see how kind of we can use this for regression? Or is that a mystery still? Okay. Find the nearest neighbors, take the average, okay, or perhaps a weighted average based on if this is my query point. If these are my nearest neighbors in the XY plane, if I want to do a regression, maybe I should count this, weigh this point more because it is closer, okay, and this one should get weighed less, and this one is kind of moderate. Okay, so I could either just average the target values of these points as my prediction, or I could average them normalized by my distance to them. Okay, any questions about it? So given this, I can do regression using nearest neighbors. The key to doing nearest neighbor classification, okay, in a robust manner involves taking more than one nearest neighbor, okay? The good thing about nearest neighbor classification is that it produces a nonlinear decision boundary. The bad thing is each individual, if you just take the label of your nearest neighbor, okay, that is not going to be, that's going to be very, very sensitive to an outlier, for example, okay? More robust thing comes from voting, taking the k nearest neighbors and assigning the majority label to it, okay? So here's an example on my height weight data of what happens if you try to do nearest neighbor classification for different values of k, okay? For k equals 1, I got this boundary situation here. Okay, notice that what my what you can think of it as being is my points carve up space into regions where every point in the plane has a closest point as its neighbor, has a closest one of these training examples as its neighbor. Okay, under those conditions, okay, here was the boundary I got for taking one nearest neighbor. What do you see when you look at this boundary? Do people kind of see what these regions mean? What is this big red region here? Why is this big red region there?
Because it's basically a straight line from that singular red point.
Well, it's this singular red point. It was in some sense an outlier, an unusually heavy and tall woman, it looks like. It was out in a space where we didn't have very many training examples. Does everybody see that all the points in this red region here have the same nearest neighbor? Okay. So according to our nearest neighbor model, any point in this region is going to have this as its nearest neighbor. And if it does, then this one outlier point has a big impact on the decision space. Does everybody see that? When I am forced to now vote, where are there points where I'm going to take 3 nearest neighbors, okay, and say I'm going to assign the majority label, okay, at every given point, okay? Suddenly this big blob goes away, okay? There still are kind of weirdnesses. There's certain islands here, an island of blue and an island of red. Why is this island of red here? It looks like this point and this point over here, there's a world where you've got a red, blue, red. All the points in this window, okay, have 2 red points as neighbors, okay? When you take a larger k, your decision surface, here we had k equals 10, becomes a lot smoother, okay, and probably more morally justifiable. Any questions about that? So using a larger k, okay, gives you a what you call it, a more robust decision boundary, okay, than k equals 1. Any questions?
Yes. So is it sort of like a tally when the k is higher, where you have one of these groups and some of the other group in
So
that
what you're gonna do? Okay, I'm not sure I know. Say that again.
So take that outlier red point that we were looking at earlier, but at the k equals 10 graph.
So at k equals 10, this point is still here. But what is going to happen if I give you a query point? that was really close to that outlier. Before here, I would say this point has to be female because its nearest neighbor is a female. Here, I would say, yes, my nearest neighbor is female, but my 10 nearest neighbors, which were 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I think those are my nearest neighbors. It looks like 3 of them are red and the rest are blue, right?
Yes.
So I'd say by a 7-3 call, this over here has to be blue.
Okay.
Okay, any questions about that? Again, when you take a larger K, okay, it is going to be, in some ways more robust. On the other hand, it's also going to be less sensitive. Okay, what if we chose K equals N? What if we gave it the label as the majority? If we had K was all, we looked at all the neighbors, all endpoints. Nearest neighbor classification will be reduced to just always saying the majority class. Okay, any questions?
Is there a preference for K to be an odd number rather than an even one?
The advantage, I guess, of being an odd number is that you always that if it's a binary thing, you will always have one number larger than the other. So generally speaking, I guess K being odd is probably good karma. If not, you've got to decide what you're going to return on a tie. Okay, so generally speaking, yes, I see why you would usually use for binary. If it was binary classification, you would use a odd number. The reason I like nearest neighbor things is it kind of gets you the idea of thinking about analogies. Okay, in a lot of fields of science or medicine or something like that, we are used to thinking about analogies. When you're a doctor, when you walk in to see your doctor, they see this patient with these certain horrible symptoms. What do? They often think, well, let's see, 3 years ago, I had a guy that looked like him, okay? And that patient died. So, this guy has no chance, okay? They usually look at, try to find analogies with other cases. In pricing real estate, nearest neighbor methods are exactly what brokers do. They say, what are the houses that are like this one in my neighborhood? And I'll give an average of that as being what my price prediction is, okay? So a lot of fields we worry about building analogies, and I happen to find it very, very insightful. And again, you're probably tired of hearing me talk about baseball, but there is one example of nearest neighbors that I always find very compelling is they compare baseball players by what players were statistical records were most similar. This gentleman is the best baseball player alive today. Okay, what does this show us? This shows us what were the names if we view their records as points in a certain number of dimensions. If we looked at the dimensions at the points for representing every player of similar age, what players are most similar? And all of them are great players, if you know about anything at all about baseball. When you look at when did he start being recognized as a great player? By the time he was 21, his most similar example was somebody who nearest neighbor was a great player. Okay, this gives you, again, I really like the idea of viewing things in that way. Any questions? I think making analogies and thinking about things in analogies is a good idea. Any questions? So nearest neighbors methods are good, but one thing I have glossed over is the running time. Suppose, let's say, I have n points in d dimensions, and I now give you a query point what is the time it takes to find the nearest neighbor of my query point? Okay. What's interesting is if you do it by brute force, okay, by comparing all endpoints against the target, if these are points in d dimensions, each distance comparison takes d. It takes n times d time to find the nearest neighbor by using brute force. Nearest neighbors methods are kind of a funny thing. The training time for nearest neighbor methods is nothing. You just basically have your points. The evaluation time of nearest neighbor methods, unless you build a sophisticated geometric data structure, okay, can be, can be very expensive, okay? So the downside with nearest neighbor methods is actually getting an answer, a label for a query given point can be expensive, okay? So we need to be worrying about data structures, okay, if we're going to be doing this efficiently in high dimensions. Any questions about that? The mother of all data structures for doing nearest neighbor computations in between points are things called Voronoi diagrams and KD trees. A Voronoi diagram is an explicit drawing of where for every point we define the region around it, where for every point within that region, the same source point is the closest neighbor to it, is the closest, has the same closest input target point. I think I said that badly, but again, we're given as input a set of points. The Voronoi diagram carves the space into regions such that 2 points with the same region, that the region you're in tells you which of the input points is the desired target. Okay. So suppose we have a world where we've got 2 points. What is the Voronoi diagram of 2 points? If I want to carve the plane into regions, right, that I know one region is for the stuff that's closer to A, one region is the stuff that's closer to B. What would such a region, how would I carve it up into regions? So anybody see kind of what my issue is? I'd like to, if I only have 2 points that I'm interested in querying against, and I want to divide the world into points that are closer to A than B and points that are closer to B than A, how do I find a separator for them?
The midpoint, and then you take the perpendicular.
Find the midpoint and take the perpendicular bisector. Does everybody kind of see that that's basically what's happening now? If I have the perpendicular bisector, all the points on this side lie closer to A, all the points on this side lie closer to B. If I take the appropriate network of these perpendicular bisectors, I get a Voronoi diagram. And the Voronoi diagram is quite interesting because you can actually, for low dimensions, you can compute it pretty quick. And finding what the nearest neighbor is to if I want to find what is the nearest neighbor of me, what I really now want to find is which cell contains me. And it reduces the problem of finding the nearest neighbor point to, given a point, what cell is it in? Okay, so Voronoi diagrams are interesting things. For higher dimensions, there is a data structure called a KD tree that kind of carves space up by giving, basically drawing a plane through the points. And it's building a tree that says the first, at the root, I'm going to go make this choice. If the region that I want, if the point that I'm looking for, if my query point Q is here, how am I going to find it? Well, I take my first plane, and I then ask myself, is my query point to the left or right of that? Given that it's on the left, I now go down the tree, and at this node, I've got another kind of plane or dimension to split. And I ask myself, am I above or below this line? And if I do that, in this case, I am above it, okay, which I'm going to say is to the right. And now I'm going to ask myself, am I above or below this point? I mean, to the left or right of it? I'm on the right of it. Now, am I on above or below this? I'm below it. Does everybody see that by building a tree of divisions, okay, I can carve space up into rectangular regions. And when I do that, what you call it? I can find kind of the nearest neighbor, the cell containing a point, basically by following a tree of depth log n, okay? And so, so certain data structures like KD trees and ball trees, okay, are good ways of trying to find nearest neighbors in modest numbers of dimensions. Any questions about that? Let me talk about one very powerful method for finding nearest neighbors in high dimensions, or near neighbors in high dimensions, that's become very popular, is a technique called locality-sensitive hashing. What is the idea in locality-sensitive hashing? Well, hashing, if you remember, was a great way. What was hashing? If you remember how we built hash tables, we had a hash function that would operate on a data value and return some value of y, some integer. If you had two items that were identical, when you hashed it, you got the same y. And in the Wythe bucket, you would have this value of s. So a hash function is something that normally, that basically maps a arbitrary key or array or vector or point, okay, into an integer. We used it for speeding identical. Is this guy in my data? Is this very point in my data structure? We use that for building hash tables because if I called it on the same point, I always got the same answer. Locality-sensitive hashing is a kind of special class of a hash function that takes 2 points, okay? And this hash function will have the property that if A and B, these 2 points are nearby, it's likely they're going to have the same hash value, okay? Normally, when you were dealing with data structures, if you were hashing skina and skiing, let's just put a G instead of an A there, you would get wildly different values. With locality-sensitive hashing, we would like to be able to say that similar points, similar strings get thrown into the same bucket, okay? Any questions about that? If so, if we had a good locality-sensitive hash function, finding the nearest neighbors should then be easy. I build a hash table of all my points where they go into the appropriate bucket. I then take my new point query and I hash it. I will go to a particular bucket. The points in there are likely candidates for being a near neighbor of mine. And so I can explicitly do that test. Any questions? The hard part is how can we construct a function, a hash function, that will give us, that if I give you two different points, P1 and P2, how can I get a hash function such that the hash codes of P1 and P2 will likely be the same if the points are near each other? Well, one idea, okay, is to use random planes through the origin, okay? Let's say that we are dealing with vectors, not points, so everything lies on a unit circle, okay, in however many dimensions we have. Suppose I build a hash code one bit at a time by identifying a first random vector, a random line, let's call it L1. And now for every point, I'm going to make the first value of my hash code be a 0 if it lies above that line, and a 1 if it lies below that line. Does everybody kind of see that? If so, all of these points will have the same first bit of 0, and all these guys will have the same first bit of 1. Okay? Now, suppose I take a second random a line through the origin, and I call that L2. I can now add a second bit to my hash code based on whether it lies to the left of this or the right of this. All of these points are the ones that lay above the first one and to the left of the second one. And so these all got the same points, the same hash code so far. These all got the same hash code so far. These all got the same hash code, and these got the same hash code. Does everybody see that if you have the nearest neighbor to a point is presumably going to be the next, its neighbor on the circle? Large hunks of the circle are given the same code, okay? And if we keep doing this with D random planes, we come up with a D-bit hash code, okay, for every point. The D-bit hash code can be interpreted as a number from 0 to 2 to the D minus 1. That defines the buckets, okay? And my claim is that if you took these points at random, the nearest neighbor of a point is likely to lie in the same bucket as the point itself, okay? Any questions about that scheme? For people following that kind of scheme, this is a very clever idea, okay? And so using this kind of a method, we can find the nearest neighbors. We can quickly find nearest neighbors by just building this hash table and looking explicitly, instead of against all endpoints, we look against the ones that are in the same bucket, okay? Any questions about that? Any questions about locality sensitive hashing and how you find near neighbors or nearest neighbors at all? If not, I look forward to reading your projects and progress reports, and I will get back feedback to you as soon as I can. Any questions? Okay, if not, thank you for your attention, and I will see you next time. Okay, bye-bye.